Okay, cool. Go ahead.
share my screen?
Mhm.
Advance screen, entire screen. Can you see?
Yeah, I can see.
Okay. So our team has made a few improvements, which are this one, sir. I managed to get an API key, but from open root service. So this ORS key is for generating the root apa? The jalur
Route.
for the map.
Okay.
Okay. And then there are also a few improvements such as this one. I inputted a define get root function,
Okay.
which is the start and the end. So start is where the the first location of the user, and
Okay.
then the end is where the user wants to go, like
Okay.
that.
Can you demonstrate?
Yes, of course. And also to make this apa program more efficient, yeah, I only focus on Surabaya first
No
rather than
problem. No
Indonesia.
problem. No
Yeah,
problem.
okay. Yeah, again we use, for example, this latitude GMs. Nanti bintang 2023. So assume we're at, yeah, in Jemur lah ya, sir. Here.
Okay.
This is the latitude. Copy,
Copy.
paste. Now this is the constraint as like the previous one. Wait for distance. Let's say 0.1. So we don't really care about distance.
Mhm.
Error. Oh, sorry. Pakai koma.
Hmm.
Oops. Sorry.
Okay.
Sorry.
Coba 0,9 pon.
Apa?
Coba 0,9.
0,9. Oke, bos. Berarti orangnya nggak mau jauh-jauh. 0,9. For rating, no, let's say 0.9 also. For review, 0.9.
Okay.
And for the price, so if the price is 0.9, which means you uh, care about the price, so it means you will get the cheaper price. If 0.1 berarti harganya semakin mahal, nggak apa-apa.
Okay.
Assume 0.1. Now this one, do you want to search based on your preference? Yes.
So you already have
Let's
map, place map HTML. So you open that. Okay. Okay. Okay.
It seems that the map cannot generate insert the on our preference here.
Actually, you already developed this one, so you generated already.
Wait, unstable.
There, those are the places, right?
Yeah. These are real places.
Mhm.
But for the ratings and reviews, I still cannot use the API key because it must pay. That
Okay.
is why I made improvements on the ORS.
Yeah, it's okay.
Let me try another number, yes, sir.
Okay.
Sir, do you think it's better if we just put like 1 until 9 instead of 0.1, 0.9?
It's better if you don't need to type.
Oh,
So
okay.
you have a default value, and
Uh-huh.
then you just need to change the value if needed. And then it's better if you use graphical user interface rather than. So you click in the map.
Mhm. Oh, wait.
So this one no need to type, and
Just click in the map, yeah.
yes, and then put radius.
Oh, in OSM,
You can just put some default value.
such as, you mean like,
Say you put in here, and then you set a default value, and then you can deal with that.
click random.
Say, for example, you click random.
Oh, cannot.
Why cannot? That one, the latitude, longitude is already there in the address.
Address.
Yeah, in the address bar above. Can you see?
Address.
Let me show you.
Oh, oh,
That is your address.
oh ini.
Yes. That is the longitude and latitude. And that is the scale. Map scale 17, that is the scale.
Oh, so copy this one.
Oh. Actually, if you can make it interactive here, that's better rather than keep typing. Right?
Yeah.
The same thing with this value. So you already have default value. And, just make it the graphical user interface nicer. Yeah, that's not so important, but make the life convenience.
Loh, nggak bisa ya?
It's already there. It's already inside your map, place map HTML.
No, I mean apa root kok nggak muncul ya? Kemarin padahal bisa loh.
Oh, I don't know that. You don't make that. So the route still not working. You will present again.
Um, let me stop share first, sir.
No problem. So you probably make a video and then you make that video as your submission. That's fine also. Just put it in YouTube. It's okay.
Okay.
Share the link only. Is that okay?
Yes, sir. Okay.
Okay. So
For my group, is it fine?
yeah, you said you are already presenting, so
Yes. Okay.
it's fine then. No problem. Okay then. So let's start with our class. So this is OR. Okay, so we discussed today two things. One is maximum flow problems, and then the other one is IFN. Okay, ideal flow network. Okay. Can you open your slide on maximum flow?
Sir, I will try to improve now ya. Coba-coba lagi. Siapa
Yeah,
tahu bisa.
later is
I will kabari you ya.
yeah, it's okay. Okay. Let's do what is called maximum flow problem. We have recorded this. Okay. Can you find the slide?
Yes, sir.
Okay. So, the maximum flow problem. Okay. So, given certain network connectivity with some source, one source and one sink. So that means similar to shortest distance last time. Okay. So you have one source and one sink. Yeah. So represent the origin and destination. Okay. Now the difference is now each link have certain capacity. So that means the capacity is the maximum flow that can pass through that link. Okay. So the problem is to determine the maximum flow that can pass the network. So be careful, this one have no demand or supply node here. So this is only origin and destination. Okay. So what's the application? So Tafin, this is the application. Yeah. So if you have oil pipeline, for example, okay, or water pipeline, okay, then you want to know which amount of oil can flow through a pipe in a unit of time, okay, but limited by the diameter of the pipe, isn't it? So the start node is the oil field, for example. The end node is the refinery. Okay? So, and then the node betweens are the pumping station. Okay. So another application is to determine the maximum number of cars that can travel through some collection of street, okay, with different capacities imposed by the number of lanes. So based on certain speed limit. Okay. So in our practice today, you will deal with this network. Yeah, this network have only how many? 5, 6. Yeah, 6 nodes, and these numbers here, okay, 3, 5, and so on. Okay, this represent these numbers here. Yeah, this represent the capacity. Yeah, imagine these are the pipe. Okay, and A is basically the origin, and D here is the destination. So question is, what is the maximum flow that can pass this network? Okay. So given the capacity of the pipe, say this is the diameter of the pipe, yeah, in certain number of flow. Yeah. For example, meter cubic per hour or something. Yeah. So again, if you remember the transshipment problems last time, okay, so this is very similar, okay, it is also similar to shortest path, right? But to solve this, okay, the idea is to make the network into strongly connected. Yeah. So in that case, you need to connect this sink node D with the source node. Yeah. So this is the dummy links. Yeah. The one in dot dot here is the dummy link. So we can solve this maximum flow problem as transshipment problem, similar. Okay, but its node has zero flow. Yeah, no demand, no supply. Yeah, that's the difference with transshipment problem. Okay, the technique is the same. So we set the link flow, yeah, for each node I to node J as X. Okay, and you know the link capacity, Cij, and then we use linear programming, yeah, like last time. So what is the result? The result will be the maximum flow in the dummy link. Yeah, the one in the dummy link, that is the maximum flow. Yeah. So what is the constraint? The same, yeah, like last time. So link out is negative, link in is positive. Okay. And then its link is between 0 to capacity. Okay. So let's put that into a formula. Okay. So these are our problems. So this is what you will do in Excel. Yeah. So what we want to do? What we want to do is this. We want to find this flow in this dummy link. Yeah, this is the maximum flow actually. Okay, so XDA, and then in its node, okay, say node A. What is the entry? Entry is DA, right? And then going out is AB and AE. So AB and AE. So going in is plus, okay? Going out is negative, yeah? Is it clear or not? So in node P, the same, okay? What is going in? AB, right? What is going out? BC and PF, yeah? So BC and PF. So going out is negative, and so on, yeah? And then next constraint is, of course, the value of the flow in AB, yeah, in AB is between 0 to 3, right? In BC, between 0 to 5, yeah? In CD, between 0 to 4, yeah? Because 4 is the maximum, yeah? This is the capacity, and so on, yeah? So, and then except the last one, which is the one that we want, okay, D to A, that one is between 0 to infinity. Okay. So up to here, is this clear or not? The formulation.
Question, sir. So, uh, by that you mean any node must have flow in and flow out.
And
Is that what I?
yeah, this is strongly connected. Yeah, that's correct.
So DA is the dummy because it's not there originally.
Yeah, originally should be having one node as source and one node as sink. Yeah, this is the problem. And then to make it strongly connected, you connect the sink to the source.
Oh, okay, sir. I
Okay.
got it. Thank you.
Okay, and then that is actually the one that you will find. Okay, the flow in that dummy link is the maximum flow. Okay, and then after that you just do linear programming. Yeah, you want to maximize the DA subject to this constraint, right? Then do like before. So what you will do, you set up the name of the links, yeah, one by one. Okay. So, and then the flow is set up initially 1, for example, and these are the capacity, right? It's given. And then the constraint for each node, use that up, of course. The left hand side, based on the formula that we set up a while ago, yeah, one by one. And the right hand side is exactly this one, huh? So this one all 0. Yeah. And then because you have capacity, so you know the capacity here. Once you set up this, what you will do, you set the objective.
Wait, sir, how do you get the left LHS constraint?
The L,
LHS
this one.
minus 1, 1.
Yeah, this one. This is the left hand side, right?
How it become minus 1?
Yeah, of course. If when this is 1, 1, 1, so this right become minus 1, right? If I set all 1, so this one, I initially
you said initially.
1, so that if you set all 0, of course 0,
Oh, I see. Okay.
right? So left hand side is this constraint. Can you see? Okay, no problem, yeah. So right hand side is all zeros. Okay. So then you set up, no? So left hand side should be less than the constraint. This is the capacity. And then this one is the left hand side equal to 0. Yeah. Then just to solve linear, non-linear as usual. Yeah. So
Sir, again, the yellow one is the manual input, isn't it?
the yellow one is a manual input. This is the one that you want to know.
Okay. And the capacity is also based on the drawing.
The capacity is based on the drawing. That's correct.
Okay.
Okay, this one, the drawing, yeah. So this capacity is given, so based on your problem. Okay, so can you distinguish transshipment, shortest path, maximum flow, critical path? They are all network problems, but they are not the same. Is it okay? And of course, the IFN later. So once you compute, so these are the results. Okay, these are the flow that will pass. Okay, and the maximum flow is actually 7. That is interesting. The maximum flow is 7. Okay, but in each pipe, okay, AB is 3 and then AE is 4. So here you can see sum is 7. Okay. So there is a theorem. The maximum flow is the same as minimum cut. Okay. So that is a Floyd-Pockleton theorem. Okay. So in here we just show not the mathematics, but just practical way to compute. Okay. So is it clear? Let's try. Okay, I will give you time to try this. Okay, once you finish, you share your screen, yeah.
Ini just
So this one is, so this is the formula, sir. XDA for XAE is XDA minus XAB
Yes.
minus
You are
XAE.
in which node?
XAE.
This is in node B.
Yes.
Okay, so node B you have going in is AB.
Mm-hmm.
Going in AB is positive, right?
Oh,
Okay, that is positive. And then going out is BC negative.
BC.
BC is negative.
BC is negative.
And then going out is PF negative.
Minus XBF.
PF is negative. What is XDA? You don't. Okay, or there. Okay, enter. Right.
XAE is this one, right, sir?
Yes.
Uh,
AE. So in node A, can I see the node A?
mm-hmm.
No, go to F. No, E.
F.
E2. Can you go to
E2 here.
no in your cell E2?
E, okay,
Can you?
there.
Yes. So you have XDA, that's correct, minus
Mm-hmm.
XAB minus XAE, that's correct. Okay. So now in node C, what you will do?
In node C is equal,
Going in is
X,
BC,
yes,
and then
XBC,
going in again EC,
XEC
okay, and then going out is
minus
minus
XCD.
CD. Yeah. Okay.
for
Yes.
for the XDA itu rumusnya apa, sir?
XDA. No. What is the formula for what?
Nggak perlu ya?
No, XDA is the one that you want to find.
Tapi kok katanya objective cell must be a formula.
Yeah, objective cell must be a formula. So where is your XDA? There. Oh. You put the value in XDA as any number first. So for example, 1, no problem. So where is your XDA?
No, this is Cedric's.
Oh, this is Hendrik.
You, okay.
Oh, you want to share your screen so that I can see? Okay, wait. Close first. Let me see. Close first. Can you close first?
Close this one.
Close first. Okay. Can we go to what is this? E15. Okay, you did not give name yet.
Yep, I don't give name.
Okay. You don't give name is easy for you, is okay? No problem.
Yes.
Okay, so no problem. Then where is your solver a while ago? So E15, you want to maximize by changing cell E7 to 15 to 15.
1 to 15.
Right. Okay, and then subject to constraint E7. Where is E7? E7 up to 14 is less than capacity. Okay, and then this one should be equal. This one, the second constraint should be equal, not larger than, isn't it?
Nah, ini yang E, sir. Second constraint yang ini flow-nya kan harus bisa dari 0.
Okay. Second flow.
Enggak ya?
No. What is the flow? That one no need because you already put it here. No negative. Delete, yes. And then
Oh.
there you found this. Yeah, so you get it.
It's 0 point. It's fine.
Yeah, it's fine. See,
Okay.
it's correct, right? 7. Yeah. So you got that. Okay. Okay, that's it. You see? Is it clear or not? So how about the others? Gavin, Devon?
Wait, sir. The XTA we inputted no formula, but we add constraint what infinity or
Okay, no, show your screen. I will help you.
okay, I will. Where is my Excel?
Sir.
Okay. So this formula is, I assume, is correct, right? Set the objective is okay, and then changing cell. This one is not correct. So until 10, that one.
Oh, okay.
There, like that.
This one also
Okay,
tadi.
that I think C. No, that is correct.
Okay.
Until 9. That
It's
one is
it's 7.
it's what is that? 2 until 7. Okay, that's correct. So you just solve.
Oh, okay.
No. Something is wrong with your constraint, probably. It's so, but either your capacity is wrong or your constraint is wrong. I don't know.
It's your laptop fault.
No. if you if you can keep name, that is easier to check. If using coordinate, I think it's really hard.
Okay, okay.
No,
Notebook
not
cannot
that
use at
one.
all.
You put it this way. Wait, I will tell.
In this one, yeah.
You highlight this.
Yeah, yeah.
Okay,
Apa?
the two of them.
And
Yes, and then go to a formula.
oh yeah.
Okay, create from selection. There, create.
It from selection.
Yes, left column. Let's click OK. Replace yes. Yes. Okay. So Now here you can give the correct name, that easier.
Equals XDA
X, which
Yes.
one? A is XDA minus XAB minus XAE, right?
Yep.
Okay. Then
equals XAP
minus BC and BF. Okay. And then in C, plus. Oh, there's a problem with the formula. Why?
wait. XAA
No, not that one. This one.
X
Not the label, okay? The values. In C, you have BC plus AE
BC plus AE
X XBC. You just type XBC, right? And then minus with CD. No, that one is not correct.
Hmm.
It's positive, that one.
X plus XBC
Yeah, XBC plus XBC
and then
minus CD.
minus with CD.
Okay. And then in D, you have only plus XCD and
Plus
then and then plus again with FD, right?
FD, yeah, FD.
D and then minus with DA. XDA.
Yeah, XDA.
Yes. And then in E, where is E? Going in is AE,
Minus
going out is EC and EF.
EC minus XEF.
Yes. And then
X
in F, you have
BF.
going in from BF and EF, going out is FT.
Yep.
Okay. So save this. The capacity, is it correct?
355,647,23.
The
Okay.
CD is okay. Yeah. Okay, just solve again.
Parameter this one, changing this one.
That's
Set,
okay. That's
set.
already correct.
Okay.
Okay. Oh, okay. Almost. This is almost 7.
Almost 7.
Yeah,
Yeah.
this is almost correct. Yeah, just round.
Yep.
Yeah. So this is correct. Okay.
Okay. Thank you, sir.
Okay.
Sir, let me share mine.
Okay.
Can you see?
Mm-hmm. Oh, you get 7. Yeah. Very good.
I got 7. Right. Okay.
Right. Okay. Wait. Why the constraint is all 0? Is that correct?
Mhm.
Oh, yeah. Okay. The constraint is all 0. Okay.
Okay, sir.
Okay. Good. Good. Taran,
Yeah, sir.
can you share your screen? Is it working already?
Oh, yeah. Wait.
Oh, working. Okay. So can you go to G4? Cell
G4.
G4. Cell G4. Click. Okay. Oh, Peter, this is very hard to. Okay. Um, it's better if you use name, you know.
Oh, yeah, sir.
Yeah. So anyway, that's okay as long as you can get the correct result. Yeah. Okay. So good. only Devon, but Devon is not there. Okay, let's do our next topic. Okay, this is the last part, which is about ideal flow network. Yeah. So,
Yes, sir. Do you call me?
yeah. Do you want to share your screen, Devon?
Oh, okay. Wait. Sir.
Mm-hmm.
Sir. Yeah, actually, I just finished my code.
You want to share screen?
Yeah, is it okay or later aja?
Yeah, it's okay.
It's okay.
Let's go, Devon. Let's go.
This is. Aduh, ini apa cara minggirnya? Okay. This is the code.
Okay.
Where is the run?
Tapi katanya kurang cocok saya sendiri.
This one ya.
Okay.
Kok kayak ini?
They're up in the address.
Okay, so nggak masuk ya. Is my voice clear?
Yeah, it's okay.
Okay. So let me input 10 ya. So the user wants to find the apa?
Closest.
Pokoknya dekat berarti caranya. And then for the ratings 10.
You should put the meaning of 1. What is the meaning of 1? What is the meaning of 10 so that people will understand.
If for distance, if the user inputs 10, berarti the user wants to find the shortest range of the place.
Yeah, exactly. So you just need to write down there.
Oh, in here, here.
Okay, 10, 10, 10.
Okay. And for the ratings, means the user care about the ratings as well as the reviews. And for the price, if the user inputs 10 for the price, it means the user does not want an expensive price.
Okay. Why you need to make again?
This one. Kan, sir, this one is the place.
Okay.
Nah, this is the place of, ini kan locationnya yang pertama tadi, di
Okay.
ini. This is the place yang di generate, and then we can see the route itu using this. Ini rute
Okay.
asli ini, real, like GPS.
Okay, good.
Yeah, just like that.
Yeah. So you just continue developing that, okay?
Okay. Actually, my concerns are ini sih. I want to make it like a GPS, but it needs apa namanya? Hardware apa gitu? Like something.
Your mobile phone have GPS.
Oh, oke. So ya, kalau basically sebenarnya Discord itu buat orang kalau nggak tahu nama tempat, nggak tahu di mana. So the user can just input based on their preference gitu aja sih.
Okay.
Oke.
Okay. So
Yeah.
good.
Thank you, sir.
Thank you. How about the max flow? Do you have a
Oh,
problem? No time.
Max Flow tadi I just ask Cedric sih. I asked him to explain.
Okay.
Okay. Just continue is okay, sir.
Okay.
Okay.
So let's continue. Okay, with the ideal flow problem. So you can go to presentation. So what is the file name there in intro? Okay, so let's start this presentation. Okay. So yeah, last meeting, I gave you some introduction of IFN, right? I hope you still remember. So let's continue. But what is IFN? Yeah, what is ideal flow network? It's a steady state relative flow distribution in a strongly connected network. Yeah, this is the same like maximum flow a while ago. Okay, which is also strongly connected. Okay, irreducible and pragmatic. Yeah. So the flow in is exactly the same as flow out. So that is exactly the same like maximum flow a while ago. Okay, but we continue that. Yeah? From that maximum flow, we continue that. Okay, and you can see the Python code already in GitHub and also Excel. You have it in Lentera. And today we also will play with the IFN tutorial in the Revoledo. Yeah, you can also access this using mobile phone. Okay, so why are we using IFN? Yeah, because even though initially it was developed as for mainly for traffic flow, okay, but it's actually used for modeling metaphor. Yeah, so the name convention is just about traffic flow, but it can be applied to many other applications. Okay, not just for traffic. Yeah? Last week I show you that IFN can be applied for various application, yeah, including AI, robotic automation, health science, and agriculture. Okay, so as long as the problem at hand can be formulated as flow equilibrium in the strongly connected network, then you can use IFN as your modeling tool. Okay, so these are the advantages of IFN. So it's already you can get directly long-term stable equilibrium. Okay, and the computation is based on maximum entropy principle, and the flow are already conserved. Okay, and this is based on network structure. Yeah, and we can have other equilibrium as well. We can get later. Okay. So what's the limitation? Yeah, if you this is not panacea. That means not all problem can be solved using IFN. Okay, if your problem is not in system in equilibrium, okay, if your problem cannot be represented as flow in the network, okay, or the network is unconnected, yeah, so not connected, you cannot use IFN, yeah. So there are 4 assumptions that you need to use to be able to have IFN. So number 1 is network must be strongly connected. Number 2, the flow must be balanced, similar to max flow a while ago. And then number 3, this must be Markov. Yeah, the decision is in its node. Yeah, local information based on neighborhood, similar to CA. Okay? And then steady state, yeah, meaning long-term equilibrium. Now, these are the characteristic of IFN. So again, reducible, preservation of the flow, and relative flow. Yeah, you can scale, go up and down, okay, by multiplying the whole network. And fully utilized network, that means all link flow must be positive. Yeah. So with this, what's the meaning? Yeah? Irreducible means the network is strongly connected. So from any point of origin, you can go to any other nodes and then go back. Yeah? So there must be a path between each pair of nodes. Yeah? So philosophically, this means integrated, unity, wholeness, yeah, some feedback loop. Okay, that also means long-term system thinking. Okay, while and this is an example of strongly connected network. Okay, so from A you can go to D, C, B, and back to A. Yeah, from any node you can go back, go anywhere, and then go back to the same node. Yeah, but how about this one? This is unconnected network. So this is the problem that we cannot solve using IFN. Yeah, because the network is unconnected. Yeah, even though A, B, F is strongly connected, similarly D, C, E is strongly connected, but the two are unconnected. So in that case, cannot be used. Yeah, and this is called weakly connected. Yeah, so A, B, F is strongly connected, right? D, C, E is also strongly connected, but you see from this right component, yeah, can go to the left component, but cannot go back. So this is called weakly connected. Yeah. So weakly connected, you can connect with the cloud. Yeah. So remember, this is the sync. Okay. So you can put to the cloud, and then from the cloud you can go back to the source. Yeah. Source component. So in this case, you will always create a strongly connected path with the help of the cloud node. Okay, so philosophically, we will say, if you are weak, okay, connect to the cloud, which represent something infinity beyond you with this probably card, and then you will become strong. Okay, something like that, metaphorically. Okay, so this is an example of weakly connected again. So if you separate, you can cut in here. So if you cut here, you will have 2 components. Yeah? This is called reducible. So if you want to make it, how about this one? This is strongly connected or weakly connected? What do you think? Is this strongly connected or weakly connected?
Strong?
You see? Hmm. Is this strongly connected or weakly connected? Why this is strongly connected?
Hmm. Strongly connected if it's looping or
Yeah, I can go from anywhere, from one node, I can go anywhere and then can go home. So from A, I can go
oh
to
no.
F, but can I go home?
Weak, sir. Weak.
I think it's weak, sir.
Weakly connected. Okay, so this is why weakly connected.
Because cannot go back to A.
Correct. So there is a component here, which is a sync component. Can you identify the sync component? This is a sync component, isn't it?
Yes.
So from A can go to this component EF, but cannot go home. Yeah, it looks like strongly connected, but this is not. Yeah. So this is so how to solve this? So you connect. Yeah, you create a cloud node here. Okay, and then you connect to this cloud node, and then from here you can connect to A, then become strongly connected. Yeah. So you create a dummy links. With the help of the cloud node, you can create a strongly connected. Yeah, but this is weakly connected. Is it clear or not? Yeah. Yeah. Be careful. Yeah. So how I know? Okay, this is the linear algebra now. Okay, how do I know that this matrix is actually weakly connected or unconnected? Yeah, unconnected means reducible, or weakly connected is reducible. Strongly connected is irreducible. Okay, so the test, okay, the test of any matrix, yeah, is called reducible. That means unconnected or weakly connected. If there is a permutation matrix P, so that I can multiply. Do you remember this? This is similar to your model matrix a while ago, but this is transpose instead of inverse. Okay, if you can find a permutation matrix that can create like this form, okay, with a zero something in this part, then this is reducible. Oh, very complicated. The definition of reducible is actually complicated. Yeah. So you need to find the permutation matrix. So easier to find the strongly connected. How? This one. Okay. So your A a while ago, so you plus with the identity matrix I, and then you exponent to the n minus 1. Yeah. If all the elements in this matrix, yeah, in the left hand side here, is all positive, yeah, no zero, then this matrix A is irreducible. Yeah. This is exactly what I use in the program. Yeah. So, okay, this is the example. Okay, so you have a matrix like this. Okay, a while ago, this is the example. We know that this is reducible, right? So this is the adjacency matrix. Okay, and what we will do? How many elements? 6 elements, right? So n minus 1. So 6 minus 1 is 5. So we exponent with 5. Yeah. And then you will see, oh, there are some zeros. Yeah. There are some zeros. That means this is reducible, yeah, not irreducible. So this is weakly connected. So this is in the form of reducibles. You have zeros here. Okay. So this is actually weakly connected. Is it clear or not?
Yes.
Okay. Okay, yeah.
Sir,
Ah,
I I think in the beginning you mentioned about maximum entropy, yeah, sir.
okay, okay,
What is that, sir?
okay. You want me to explain maximum entropy now? Okay, I can explain. So wait. Let me. Okay, okay. I can stop this first, and then I will explain maximum entropy so that you will understand. Okay. Let's open an Excel file. We will open Excel. Can you see? So I have A, B, C, D, E. Okay. Let's put any number here. Is that okay? Let's put any number. So what's the number?
Are you sharing your screen?
I think so, but you cannot see.
It just blank in my screen. Okay.
Okay. So here I will put any number. So any number that you like. I will put 7, 9, 15, so 20, 32, and 17. Okay, so that okay, I will put it here so that you remember this is my numbers. Okay, I will put it here. This is actually our number. Secret. Yeah? Secretly we record. Yeah. Okay. And what we will do is we get the average. Average. And we can get the sum if you want. Okay, these are the statistics, isn't it? So I will get the average of this value. Okay, and I get the sum, right? The sum of this value. Yeah, these are my random value, yeah. So the same thing here, I will just copy. Okay. So right, this is our data. Okay, this is our data. What will happen if I delete this one? Suppose I miss one data. If I miss one data, what will happen? The average change. But if I know the average supposed to be 16, what is the value here? If I know the value, the sum must be 80. Okay, so now it's 63, right? So what's the value here?
17.
Yeah, you just minus, isn't it? 80 minus 63, you will get 17. Then I get back. Okay, if you have only one value missing, okay, you can get that from the statistics. Okay, you can get back that value. Why? Because the degree of freedom of sum or average is actually 1. Right? So we call it DF, statistic, yeah? Degree of freedom. Okay. So if you, what's the meaning of DF or degree of freedom? That means if you know the statistics and you miss only the same as degree of freedom or less than, okay, then you can recover back your data. Yeah, that's the meaning of DF, isn't it? So what happens if we know the degree of freedom of sum is 1, okay? So DF is equal to 1. But now what happens if I miss 2 data? Can we recover these 2 values so that I can get back this one?
Yes, but there are a lot of possibilities.
Exactly. So now, okay, there are a lot of possibilities, right? Now we want to use a method, okay, or an algorithm so that using the least possible assumption, then you can get back that information. Okay, so what you will do, okay, what I will do is I will calculate the probability. Okay, so how to calculate probability? Any value I divide with the sum will get the probability, isn't it? Okay, so what I will do is I create the probability. Okay, this is 0. Okay, so I will calculate the sum plus 1, right? So then from this probability, I will calculate what is called entropy part. Yeah? Entropy part is not the entropy, it's just a part of the entropy. So how to calculate entropy part? Entropy is just minus of the probability multiplied by ln of the probability, isn't it? Okay, so as simple as that. Okay, but the problem is if we compute this, because ln of 0 is not defined, so there is some problem there, right? So then you add if error, yeah. So here if error, yeah, then the value is 0, yeah. There I add this. Oh, so then I can calculate the entropy. Entropy. What is the entropy? Just sum of that entropy part, isn't it? There. So I want to get what is called maximum entropy. Okay. So I will use solver. Oh, I need to install my solver. Wait, it will take some time to install solver. Solver. Yeah, it will take some time to install solver. So, so you can start to do the same, can you? While I'm installing my solver. Okay, so I have the solver here already. Oh, there. Okay. So what I will do is I create the entropy. This is the entropy, right? T10. Okay. And then what I want to change is this value here, the one that missing, isn't it? I want to know the value that is missing. Okay, subject to constraint. What is the constraint? The constraint is the average must be the same as 16. Okay. There, I will run this. Da-da-da, I found the solution. Oh, see? Okay. Not exactly the same as our initial, but you will see it will produce exactly what we want, the statistics. Can you see that? So maximum entropy, yeah, is an optimization, right? You want to maximize the entropy, okay, to find the missing value, okay, with the least possible assumption, okay. So of course, in this case, you will get uniform distribution, okay, in this case, but not necessarily. So the same thing, suppose I don't know this, yeah, suppose I miss 3 values now, okay, if I miss 3 values, okay, so what I will do, the same thing, yeah, I will maximize the entropy, okay, now changing the 3 values that I want to know, right, subject to the same thing, yeah, so the average must be 16. So this solve. There I found. Yeah, I got exactly what I want, 16 and 80. Yeah, but the value changing, yeah, become uniform distribution. Is it? So we know from the maximum entropy principle, okay, if you don't know, okay, these are the one that you know from the data, then you use that. If you don't know, then you can assume certain probability distribution. So, okay, in this case, uniform probability distribution that maximize the entropy, then you can recover the missing values. Is this clear or not?
So, sir, so does that mean that all three values should be the same?
In
Or,
this case, yes.
but is there a probability that maybe perhaps C is bigger than D or E, sir?
Possible. So then you
Possible.
need to change this probability,
Okay.
right? Because that
Right.
entropy depends on this probability that you want. For example, you already know previously this one, okay? Or based on other data, you know this previously, then you can set this. So let me set this probability. Okay. So this one is this divided by the sum, isn't it? Okay. So if you know the probability, okay, even if this is rough, okay, then you can set up, okay. So you can set up this probability here. So this one you set up not based on the data, because this is actually zero, right? So you can set up here equal to this one. Okay, this one the same. Then, of course, if you know this probability, you will get back exactly that. You want to see? Solver, solve. Where? Oh, wait. This is some solver. Changing the value of this one. Okay. So let me put the value 0 first so that you will see. Okay, and let's do the solver. Okay, we want to find this one. Okay. Oh, this is a problem because this is not related to this one. So it will just give any value. It will not solve. Yeah, it will still give the value of this because the same value because this one is not related to this one. So you need to find a formula to relate this one to this value. Or we can add another constraint. Okay, so you can add other constraint, for example, the probability. Okay, sorry. A while ago was this one, the copy. Okay, so we add other constraint, for example, here, okay, that this probability must be the same as this probability, right? And then this probability must be the same as this probability. And the last one, this probability must be the same as this probability. Okay, then solve this, then you can get that. So close. Yeah. Can you see? So if you set that probability as your constraint, then you will get back. Okay. The original. So if you know the probability, okay, then you can get back the actual value. Is this clear or not? By maximum entropy. No, question. So the same thing in IFN. Okay. So imagine you have in the one whole city, okay, its intersection, you have a probability to go straight, turn left, and turn right, isn't it? So the problem is what is the probability to go straight, turn left, and turn right. Well, you can get that from the data of the camera, for example, right? But if you set the camera in each intersection in the city, how many cameras you will install? Too many, right? Probably one intersection you will have probably 4 cameras in each direction. That means if you have, say, 1 million intersection, then you will have 4 million at least cameras, okay, in each intersection. So probably not feasible, I don't know, okay, to install the camera in each intersection. So to get the actual probability, then you need to assume, okay, if you can install all the cameras, you get the actual probability, then yes, you can get the actual result. What is the actual flow? Okay, if you don't, then using maximum entropy, okay, you can assume the probability. So one of the assumption is based on the capacity, proportion of the capacity, isn't it? So if they go out and get the higher capacity, of course, people will go to that area more than if they are very small road. Right. So this is just based on logic that if you have a wider road, okay, people tend to go there, okay, more often than if you have a small road. So this is assumption, of course, okay, not necessarily true, okay, but if you don't know, at least you can know by certain assumption. So better than nothing. You don't know, then you cannot compute. So this is the principle of maximum entropy. Yeah, if you don't know, you can still get the result. Okay, that is the benefit of maximum entropy. You can find the missing value even if you don't know. Is this answering your question?
Yes.
Okay, so you get the principle of maximum entropy. Yeah, so you can always recover the data, okay, with certain assumption. So what is the least possible assumption? Uniform distribution. You probably don't realize the uniform distribution, the essence of uniform distribution. Okay, uniform distribution means equal, fair. You see, when you have a pizza, say you have 5 people, how do you distribute equally? You divide by 5, isn't it? So when you divide, okay, by the same number, that's mean uniform distribution. Okay, since child, you don't realize that you are actually already using uniform distribution. Every time you divide, that means you are using uniform distribution to be fairly. Yeah. We just don't name it uniform distribution. You name it division. Okay, but the statistically that is uniform distribution. Okay, any comments? Okay, so now come back to the IFN a while ago. Okay, the IFN slide. Okay, so this one, this is an example, okay, that this is actually reducible. Yeah? Reducible means weakly connected. Yeah. How do you know this is weakly connected? Okay. From the A, the adjacency matrix of this network, okay, you add with the I, yeah, it is the identity matrix, and then you exponent n minus 1. Yeah, this is 5 node or 6 node. 6 minus 1 is 5. So exponent to 5, you will get this value. If this value not all positive, so there are certain value, this one is still negative, isn't it? 0, isn't it? There are certain value, this is 0. That means this is actually weakly connected. Yeah. if they are positive all, sometimes we call it primitive, that means positive. That means this is irreducible. Okay. So the next assumption is pragmatic. Yeah. That means the sum of inflow equal to the sum of outflow. This is exactly the same like in max flow a while ago. Okay. And what is the interpretation? Balance, yeah. Justice, fairness, equality. Okay. Equality here not necessarily means uniform distribution. Yeah. Just the sum of inflow equal to the sum of outflow. Yeah. So the sum of columns the same as the sum of rows. Yeah, this is the example. You will see in here 8, here also 8, right? The sum 3 here, this one is also 3. The next one is 3, so here is also 3. Can you see? This is 16, this one also 16, and then the last one is 12. This is also 12. Yeah, this represent the node values. Yeah, so these are the meaning of pragmatic. Okay, so matrix form you can just multiply with 1, 1, 1. Okay, this is the meaning of pragmatic. Yeah. So, how about this one? Is this pragmatic or not? Is this pragmatic or not? Hmm? Anyone? Stefan? No, you check. Yeah, in this node, going in is 4, going out is also 4. Yeah, the next node going in is 2 and 1, so going out is 3. Here, in this node, going in is 3, and then going out, 3 and 2, yeah. And then
It is pragmatic, sir?
yeah, this is pragmatic, yeah, because in each node, yeah, so the sum of inflow is the same as outflow. So in this case, pragmatic. Okay. You can also see from the flow. Okay. Then you can see the pattern, yeah. You can see the pattern here. This is exactly the same pattern. So yes, this is pragmatic. Okay. So now this is the simplified version, yeah. So if you have any network, okay, if the network is unconnected, then you cannot use IFN. Huh? So if the network is connected, there are two possibilities. Yeah, one is weakly connected, and the other one is strongly connected. Yeah. So if you are strongly connected, then you can use IFN. If this is weakly connected, that means you are having either sink node, source node, sink component, or source component. Yeah. So in this case, you can use cloud node, okay, to connect, okay, and then it will become strongly connected. Okay. So I hope this is clear enough. Yeah. So algorithmically, there is a algorithm named Tarjan algorithm. This will create the largest strongly connected. Yeah. So in the city network, there are so many say nodes. If you want to do one by one checking, is very long. So in that case, I just reduce. Okay, so we just use the largest strongly connected network. Or you can directly connect the source node and the sink node, yeah, or using cloud node. Yeah? These are the three methods if you are having weakly connected network, yeah. Okay. If you are having unconnected network, then you cannot model using IFN. Okay. So because IFN required strongly connected network. Is it clear or not? So the cloud node is optional. Optional modeling tool to connect the sink node to the source node via dummy link. Yeah. So you can hide later if you want. So if your network is already strongly connected, sometimes you still want to add cloud node. For what? to model external environment, yeah, something outside. Okay. But if your network is weakly connected, then you can add cloud node and the dummy links to make it strongly connected. Yeah. So in the application, if you want to create the cloud node, if you want to make IFN using cycles, okay. Remember, IFN is practically an expanded network from the cycles. That means you need to create cycles, right? Say your data table, okay? So each row you connect, okay? This is one trajectory. To make it cycle, then you introduce cloud node. So this is like the start and the end of the cycle, okay? Of course, you can hide that later. Okay, so this is the theorem, yeah? So there is only one cloud node is sufficient, yeah, to convert weakly connected network into strongly connected. Yeah, this is not necessary, but this is sufficient. Yeah. Okay. So remember, cloud node is optional. Yeah, not necessary. Okay, but this is enough. If you need to connect, then one cloud node is enough. You don't need 2, 3 cloud node. Yeah. So metaphorically, cloud node represent infinity or something outside, okay, which is we can say spiritually we can imagine this is like God. So that means from weakly connected you can become strong, okay, by connecting yourself via prayer, which is the dummy links. Yeah. Okay. So if you are having weakly connected, then first reveal, yeah, if the cloud node will make it strongly connected or not. Yeah. If you can get the ideal flow matrix, which is pretty much irreducible, then it's fine. Okay. Then you can get other matrix indicator. Yeah. And after that, you can hide the cloud node just to have better visualization. Yeah. But the computation is still there. So don't forget, you can only compute IFN, yeah, if the network is strongly connected. This is very important. I repeat again and again. So this is an example. Yeah. So this network is clearly weakly connected. We have source and sink, right? So source and sink. Yes, you can connect directly like a while ago. Yeah, from the source, from the sink, you can connect to the cloud node. And then from the cloud, you can connect to the source. Yeah, without cloud node, that's fine also. So you can directly connect the sink to the source. Yeah, so cloud node is just optional. Yeah, modeling tool. Is it clear or not? So without that is also okay. You can connect this way. So you will get exactly the same result. You know? So this one's still 2, this one's still 1, this is the still 1. Yeah, so exactly the same result. Okay. So in this intersection, okay, this other represent the capacity, right? So in this intersection, I still connect to the cloud node, even though this is actually strongly connected, yeah? Okay, why? Because look at this intersection, the traffic should come from somewhere. Okay, it's not just merely from this intersection and looping in here, right? So in this case, we still add the cloud node, yeah, to represent the external environment, yeah, outside our system. Okay, and this capacity represents the number of lanes, yeah, of its link here. Is this clear? So, okay, can you add cloud node and dummy links to make it strongly connected network in this example? Practice. You just draw and then share your screen. Can you? Hmm. Do you know this network that you
Yeah.
just draw? Okay, this represent weaving section of the roundabout below that I showed a while ago in the Bundaran HI. Hmm? So where is the one more link? From here you connect there, right? Okay, and then how do you connect? So if you want to cut the cloud node, okay, from here to cloud node and come back, and then from here, what you will do, you will also create the cloud node, the dummy link to the cloud node. Yeah, so it's better to put dummy link as dash, okay, and then the same thing here from the cloud node, you can make the dash to the other side. Yeah, is that okay? So basically, you connect the sync node to the source node, yeah, via a cloud node. Is this clear? Any question?
No, sir.
No question, yeah. Easy, yeah. Okay, let's continue. I will close this whiteboard. Is that okay? Or you still want to play? Yeah. Okay. So let's share this. Yeah. So you connect, yeah, the sync to the cloud node and from the cloud node back to the source. Yeah?
Sir,
Hey,
okay, so it's only one cloud, or can we have two clouds, sir? So, for example,
only one card, monotheism.
only one. So we must connect from the cloud.
Yes.
Oh, okay, sir.
Yeah. Easier to remember if I said that. This is a simple intersection. Okay, look at this. So, suppose I know AE from A to E is 100, and then from B to E is 200, and then I know from E to C is 50, and then from E to D is 250. So the total is 300 and 300. So I know this value, yeah. So is this pre-magic? No, right? Huh? The flow matrix here. Is this pre-magic or not? Huh? Can you see the slide?
I don't think it's pre-magic, sir.
Yeah, this is not pre-magic, yeah. So how to make it pre-magic? Okay, so you add cloud node, yeah. Look at this. When you add cloud node, what will happen? Yeah. So this is the original, right? Okay, and then you may add cloud node. What will happen? I add Z as the cloud node. Is that okay? Then there, when you add, okay. So how much? So A to E is 100 a while ago. These are given, right? And then, oh, how much is C to Z? C to Z must be continue, from here, right? EC is 50. So here should be continued. So this one become 50, right? How about the D to Z? Yeah, we know this one is 250. Then continue, yeah, 250. Okay, the same thing here. So BE is given, right? BE is 200. So in this case, Z to B is 200 also, correct? And AE is given. So AE is 100. So in this case, from Z to A must be 100 also. Okay. So in that case, once you put this, wow, suddenly become premagic. Become IFN, in fact. Nice.
Ooh, nice, bro.
Yeah, nice, yeah. So if you can get this, okay, initially you will say, oh, this is not premagic, okay, because your network is not strongly connected yet. Once you put it into cloud node, okay, you see suddenly become premagic. Okay.
Cloud node is like a dummy node.
Yes, it's a dummy node, but you see this dummy node is actually helpful, no?
Yes.
Yeah, you suddenly you can start to see, oh, they are premagic. Okay, something behind the scene is there. Okay, so what you see is not always true. Okay, there are something bigger outside you, which is in the Z. This is represent the external environment. Clear, yeah? So again, is this premagic? No, right? Okay, practice now on your own. Can you make it IFN? And then you share. Should I give one by one for each of you? So who will do this?
Me.
And then this one another practice. This is another practice. So many practice here. So you choose one. Okay, let's try this one first. Okay, can you make it? Maybe after this practice, you will get the idea. So if you use only this one, you cannot see they are premagic. But once you,
Sir,
yes,
do I have to connect from A to D and then D to C to make the cloud node below
yeah.
D, for
So you make
example?
cloud node like this.
So we have to connect all the nodes together.
Correct. Yeah. This one look like this is strongly connected, but this is not yet IFN, you see. Okay, so this is not correct yet. So once you make it with cloud node, and then you will see this is actually IFN. See, exactly premagic. Yeah. Only this, yes, this is already irreducible, isn't it? strongly connected, this one. From A, go to B, go to C, go to D can. Yeah, but this is not IFN. This is only irreducible, but not premagic. Okay, so the network below is IFN. Okay, this is irreducible and premagic. Can you see the difference? So I want you to get this value so that you will know on your own. Okay, try not to see the answer. So try on your own so that you can get the idea. So I will distribute. Yeah. So this practice, who will do? Chadrick and Dafin. Is it okay?
Okay, sir.
Okay.
Okay.
And then this practice, who will do? Daran,
Sir, me, sir.
Devon. Yeah. Daran and Devon. Okay. And then this practice. Oh, Lexan, you have 6 problems here.
Oh shit. Okay, sir.
Okay. You have 6 problems. Okay. Okay. So try. You have it, right? This one in the slide. So once you finish, please share your screen. Okay. You can share your screen, Lexan.
Actually, I don't do it on paper.
Okay.
Can you just with your screen first?
Okay, sure.
Yeah.
What number is that? So, okay, so you can
This is not mine.
this
Next
one.
one. For the A, it's not EFN yet,
Okay,
and I think it should make a cloud nodes
correct.
to connect the left side and the right side.
Mm-hmm.
Is it
Okay.
correct?
Correct. That's correct.
For the
D,
P, it's not EFN.
okay, the same. You need to have cloud node.
Yes, cloud node.
Nick.
For all of the nodes, yeah.
No, you connect the sink to the source. Yeah, this is the
Or
and the source.
the red and the top one.
So the value in the cloud node will be 2,
Yes.
right? How about C?
C, it's EFN.
Yes, C is IFN. How about D?
T, no.
Again, lack of cloud node, yeah?
Yes, need cloud node to connect the node at the very left side and the right side.
Correct.
And it's the cloud node 2, yeah. Or
Yeah, cloud node is also 2.
so. And the E picture is EFN.
IFN and F is also
Yeah, F is also EFN.
correct. Yeah.
Okay.
Okay, good. Okay. So yeah. Yeah. After this, we go here. Okay. Okay, let's can you get this already? Rafin? Patrick? And Stefan?
I'll try the next one, sir. Not that one.
Okay, okay.
Okay. Very good.
Yes, sir. Mine is which one? F.
The weaving section.
Waving. Waving. Should I share my answer?
Yeah, go. Okay. Please share your screen. Stefan?
It's supposed to be me and Darren, yeah.
Yes.
Oh.
No, you can share your screen. Go ahead.
Wait, yes, sir.
Yeah, you can next time you can also try the T intersection and weaving section. Okay, wonderful.
I do understand already, sir.
Do you understand already?
Yes.
Okay.
Sir.
Karen, you want to show?
Oh, yeah.
Okay, share your screen. Okay, this one is, so now you add,
At C.
okay, you add Z, then you are in the waving section, right?
Yeah.
Okay,
Thank you, Darren.
yes,
Which one?
yeah. So suddenly you get the result, yeah, which is pre-magic, isn't it? So you get pre-magic and irreducible, yeah. So by having the Z a separate node, okay, so you can start to separate which one is internal, the system, and external of the system, yeah. Okay, so I think this is easier to understand. Yeah, the result is pre-magic, isn't it? Oh,
Yeah.
Daran, can you check here if you want? Go. Oh, before. Can you? Do you have a IFN add-ins installed?
Sorry, sir. Apa tadi?
Do you have IFN add-ins installed?
IFN. Oh.
Okay, let's try. Can you share your screen again?
Oh, wait.
Okay. Go to any cell. Say, for example, in here. Just click there. Click any cell. It's okay.
Yeah.
Equal. You type equal n underscore. Oh, there you have it already. Okay. Can you go a little bit down? Do you have delay also? And D. You type D. Oh yeah, you have it. Okay, good. So okay, after this we will use this. Okay. So you can type n underscore is premagic. Is not delay. Is premagic. So sorry. N underscore is premagic. So you checked a while ago your matrix. Okay, so it's
This
premagic.
one.
Yes, this one you can check. This one. No, not including the sum, right?
Oh yeah.
So in this case, you have from K2, yeah, K2 until 8. Yeah. So Q8, Q until Q8. Okay. Close parenthesis. Oh, true. Yeah. And then is n underscore again. Equal n underscore n underscore is ideal flow. Yeah. Is ideal flow. Okay. Check again the same matrix and close. Close. Oh, true also. Yeah. So you can test whether this is a ideal flow matrix or not. Yeah. Okay. Good. Thank you, Karen. So how about the T intersection?
Should I go, sir?
Sure.
I think my interpretation can be mistaken. But
Problem. Let's check about that.
so is it? I think I read it like this, sir. So if
Okay.
A is getting 1,000,
Mm-mm.
it should give back to Z 1,000. I think.
Mm-mm.
I think that's the concept, right?
That's correct. Okay. So the 112. Yeah, I think it's correct. Yeah. So then you can test again here. Test in any cell that, yeah, n underscore is ideal flow. Yeah. Oh, is ideal flow.
Is ideal. Well,
Why you don't have do you have?
I think since everything is now not recommending me the function, sir. Some it doesn't give the
Oh, okay. So
equal
equal n
and
underscore is
or is flow
ideal flow. Is
or
ideal
ideal
flow.
flow.
Okay, open parenthesis and then you try. Yes, until P. Yeah, that one. Close it.
Oh
Oh,
yes.
okay. So just strangely, you cannot see the
Yes.
menu.
Is it I should
Or
is there a setting for that, sir?
probably you just ask the AI
Oh,
about
okay,
that
sir.
setting. Okay.
Okay, sir. Thank you, sir.
Yeah, thank you. Good. So you have it. Tafin, you want to share something or it's the same as the others?
I did it in my paper,
Ah,
sir.
okay. So you can
Yeah. But it's pretty much the same as Terrence did.
okay, good. Good. So Devon, no problem.
Yeah, did the same there.
Okay, good. So you can actually create okay, ideal flow matrix from non okay, ideal flow, yeah. So let's go to the next topic, yeah. So can you see my screen? So ideal flow is a relative flow. Yeah. Last week we practiced that. Yeah. So it's a rational number by definition. Okay. It's not actual flow. Remember, the actual flow when you do random walk will reach infinity. Yeah. So but once you divide that flow with the statistic of the flow, okay, that will become a relative flow. So the asymptotic value is the ideal flow. Okay. So because of relative flow, so that means it is scalable, yeah, for the entire network. That means you multiply with any scalar, so alpha, okay, then you will get another equivalent, yeah, equivalent ideal flow, yeah. So let's give several names, yeah. So I will call basis network, okay. That means the total of the flow is 1. So that represents probability, yeah, the link probability. So let's define it, yeah. So suppose you have two network, yeah, N1 and N2, yeah. Both of them are ideal flow network, yeah. So then we will say that the two network are equivalent, yeah, if and only if, okay, the corresponding flow for one network is a multiple of another by some constant, which is positive, yeah, positive constant. So, okay, when the total flow is equal to 1, so this will become basis, yeah, basis network, because this represents the link probability, yeah. And if the IFN with the minimum integer flow, yeah, in all links, then we call this cardinal network, yeah. So just remember, Cardi likes integer, yeah. So several things interesting, yeah. So all equivalent IFN will have the same stochastic matrix. The coefficient variation of the flow is also the same, okay? And then the average node entropy is the same. In fact, you can get a lot of properties, yeah, aside from this, yeah. For example, you can use relative entropy is 0, okay, and so on, yeah. You can also calculate the mutual information and so on. So there are a lot of invariants based on equivalent IFN, yeah. So these are the 4 standard form. Okay, if the total flow is 1, so we call this basis network. Okay, if the minimum flow is 1, then of course we call it unit minimum flow. Okay, and if the maximum flow is 1, then we call it unit max network. Yeah, if the all integer and with this minimum, so we call this cardinal network. Yeah. So example, yeah, this is an example. So I have this IFN. Okay, you see this is premagic. Okay, can you see? So this is premagic, and these are already cardinal network. Okay, and then I want to have the total flow of 17,500. How do I get, okay, scaling? So because this is what I want, so I set here, okay, 17,500 divided by this total 38. Okay? And then I multiply this scaling to all of this, each of this cell, I will get this new ideal flow, yeah? Which is still premagic, but scale up, yeah, from 38 into 17,500. Is this clear or not? So I can scale up, scale down, no problem. In fact, this is what we use for calibration. Up to here, is it clear or unclear? Just multiply, okay? So for example, here, 17,500 divided by 38, how much is that? Should be around 460.5, isn't it? So then this one becomes 460.5. If multiplied by 2, that becomes 921, and so on. Okay. Multiply by the same values. Is it clear or not?
Yes.
Okay, yeah, clear, yeah? We just multiply with the same value, that's all. Okay, so now suppose I have, this is basis network, yeah? Basis network means the total flow is 1, yeah? So the total flow here is 1. That means each of these positive number represent a link probability, yeah? So if you put this into LCM, the LCM of denominator, which is 49. So if I multiply everything with 49, then of course I will get this. Yeah. So the total now become 49. And this is actually cardinal network. Yeah. Because this is the minimum we can get. Okay. So assuming that there is a dummy node here and cloud node in the back. Okay, I did not show, but there is, yeah. So the cloud node and dummy links are hidden, meaning there is, but I did not show. So how to get cardinal network of this? Multiply by, what is the scaling? Anyone know the scaling? What is cardinal network a while ago? Integer. These are not integer. See, 2.5 is not integer. So how to make this integer? Multiply by?
That
By 2.
Yeah, by 2. Okay. If you multiply by 2, so you will get this. These are all integers. Yeah. Again, I have assumption it is actually connected. Yeah. So look at this. The minimum link flow in this case is 2. Yeah, not necessarily 1. You see. Okay. So this is still cardinal network. Is it clear or not? In this example, okay, which one is the basis network and which one is cardinal network? What is basis network a while ago? The sum is 1, yeah. So this is clearly, this is the basis network, yeah. So what is cardinal network a while ago?
Integer.
Integer, minimum integer. Okay. B, C, and D are all integer, but the minimum is this one, right? So this is the cardinal network. Yeah. This one is multiplied by 2 from cardinal network. Okay. And this one is multiplied by 3. Okay. They are all equivalent. Yeah. A, B, C, D are equivalent network. Okay. But different scaling only. Is that clear or not? Is this too fast or just okay?
It's fine, sir. But I think
Yeah.
you are tired already.
Yeah. Okay. So again, let's assume the cloud node and dummy links are hidden. Okay. Can you find the basic network and the scaling? Okay. Let's.
Sir, for this one, I think you multiply by 2 again. The 1, 0.5, and 1.5.
There is no basic network in this example. So let's say this is the original. So this is like the cardinal network, right? So this one is, what is this? You divide by 3, right? This one. This one you divide by 2. Okay. This one you multiply by 500. Yeah. Is that clear?
Okay, sir.
Okay, easy, yeah. So from there, you can actually calculate the flow. Okay, let's practice in Excel, you want, so that not sleepy. Let's practice in Excel. What do we want to practice? Can you go to the slide? Okay, can you go to the slide manual, IFN manual computation? IFN manual computation. Is it? Can you open? So there are how many practice there? Is it 14 practice or 13 practice? So I will give you example how to do. Okay. How to do manual computation. And then you practice, yeah. So this manual computation using hand, okay, using paper only, you can do. So first you set the origin node and then single link node. And then if this is a single link node, that means only one in link and one out link, the flow continues. Yeah. So if there is a multiple in link, you sum all the incoming flow at that node. And then if you have multiple outlink, you distribute the inflow among the outlinks based on probability distribution. Okay, so this is an example, okay, that I will use only uniform distribution. Okay, so initially I set 100. Okay, here I can set any. Yeah, so then this one become 100, right? And then in node 1, I divide equally, so now become 50 and 50. Okay. Now in node 2, what we will do is coming in is 50, so then become 25 and 25, right? Because we assume equal distribution. Now in node 3, what we will do, this coming is 25, so divide by 2. So we have 12.5 and 12.5, yeah. Node 4, there is the only one. So in this case, we continue. Okay. So this E is already ideal flow network. Yeah. This is already ideal flow network. Yeah. You see in node 5, you check, okay, if the sum of in link is the same as out link. Yeah. So now if you want to make it integer, you divide by the minimum, in this case, 12.5, then you can get the integer IFN. Yeah. So these are also IFN. Clear or not? Any question? So how about this one? So in this case, you just put 111. Yeah. So you will get the, how about this one? This one also 111. Okay. How about this one? So here you can put any numbers. So assuming equal outflow, what you will do? So let's assume. Okay, let's assume, say, for example, you have 100 here. Possible?
Mm-hmm.
So if this is 100, okay, how much is CE?
C what?
CE. Equal
100.
outflow. So CE must be
100.
correct. So this one must be 100. Yeah? How about DE?
100.
Correct. Okay. So we already know CE. How about the BC?
BC 200.
Yeah, 200. Okay. Oh, oh, if BC 200, how about PE?
200.
200. Okay, so this one also 200 because equal, right? So in that case, AB is,
400.
oh, very good. If this is 400, how about AE?
400.
Oh, very good. So this is 400. Okay. So how much is collected in E?
Wait. Oh, is it? No.
In E is
800.
700.
800.
1 plus 1 plus 2. So 400, 800. Is that correct?
Yes.
So
800.
in that case, EA is
800.
800. Okay. So you get easily.
Easy.
Easy. So you divide by 100, you get the integer, the cardinal.
Uh-huh.
Easy or not?
Easy.
Easy. Okay. So now this is the same. This is also easy.
With times by 3 first.
This is the stochastic, no? So who will, so how I will get the value? Can I put here 1? This is probability is 1/3 and 2/3. Can I put here 2,
Yes.
right? And then BA is
PA is 3.
3. Okay. In that case, CB is
2.
2. Is that correct in B that 2 plus 1 is 3? Correct. Easy. Easy or not?
Easy.
Easy. Okay. So that is the answer. How about this one? Who will do this? This is easier. So what you will do?
Right, why all nuts is A, sir?
This is the probability is given. So, name is wrong, yeah. This must be B, yeah. And this must be C. Okay. Go A, B. How much?
1.
Okay, let's say this is 1. So if this is 1, how about AC?
AC.
Must be 1. Correct? Because this is equal. Right? So if AB is 1, then AC must be 1. How about CA?
1.
No.
Uh, let's do CP first.
Huh?
CP first.
CB.
Mm-hmm.
CB how much? You don't know. You don't know the CB. How much is CB? You don't know CB, but you know CA.
Sorry, CA is 2. CA is 2.
Correct. CA is 2 because going out is 1 plus 1 is 2. So, okay.
Hmm?
It's easy.
Yes.
What's it do?
Look at the note A.
Oh, yeah.
Okay. You see or not? So it's
Mm-hmm.
a puzzle, right? So now if CA is 2, then CB must be
2.
2. Okay. So
PC
so BC must be
3.
3. But 3 plus 1 is 3. Oh yeah, correct, yeah. Out is also 2 plus 2, 4. Now you have the ideal flow.
Yes.
Nice. Okay. So you can do manual computation, isn't it? Is it or not? So you can create your own, okay? And then you can do, okay? Oh, yeah, this is the answer. Is that correct? Oh, yeah, the answer is correct. Now this is B and C. Yeah. Okay, next. Oh, who can do this? Okay, if you can do this, you can claim your recitation. Okay, from 6. Okay. 6, 7, 8, 9. 6, who will do this? Practice 6. Want to do practice 6?
Me.
Okay, Lexan. Okay, 6. 7.
Need to number 7, please.
You will do number 7. This is number 7. No, this is still 6. Oh, this is number 7. Devon, you will do number 7. Devon, number 7. Okay, and then number 8. Wow, who want to do number 8?
Darren,
Number 10, sir.
Okay, wait. Darren want to do number 10.
I will do number 9, sir.
No, okay. So how about number 8? Who will do number 8? Dafin, can you do number 8? And then Cedric, number 9.
Number-
Wait.
edits.
This is number 10. No.
I'll just do number 11.
Wait. This one, Darren, this is too easy for you. Number 10 and 11, okay, is yours.
Oh, yeah, yes.
Okay, 2. Darren, you get 2. Darren, you get number 10 and 11. Okay, do it. Okay. So once you finish, you share your screen, okay? Oh, really? Oh, what number are you?
Can you share your screen?
My screen?
Yeah, for the question.
What number? Cedric is number 9? Yeah, you have a signal, that's correct.
Yes.
So you need to put cloud node.
So that means I have to make a cloud.
So that's correct. So you have, is this your problem?
Yes.
Yes.
I have to make a cloud from C to A.
So
because-
this is have a sync node and source node. So in that case, you make this is weakly connected, so cannot be computed. Okay, in that case, you create a cloud node like this. Okay, so once you make the cloud node, okay, so now you have this. Okay, then you can start to compute, yeah, the ideal flow. Okay, so there you can get this result supposed to be. Is that okay?
Yes.
Yeah.
Okay, sir.
Very good. If you start to see that this is not okay, then weakly connected, right? That means you can add cloud node, yeah, easily. If they are not connected, you cannot solve. It's just weakly connected, just add cloud node, easy. Okay. This one problem can be solved. Do it.
Sir,
Go.
what about this one, sir?
This is 12, 3. Okay. So 9, 11. 11 going there is 1 plus. Okay. Wait, going to B is 11 and
Hmm?
look at note B.
Mm-hmm.
Okay, 12. Okay. I think this is correct. Right. So what number are you, Lexan?
The first one.
The first one. Wait, Lexan is number 6.
Yes, number 6.
Oh, what I got different from you?
I don't know.
Oh, let me see.
I'm sharing my screen.
Yeah, yeah. Oh, I got. Oh, okay. So maybe different probability that I use. Huh? 2/3. Oh, yeah. Okay. So maybe you are more correct than mine.
Are you sure?
Yeah, I think so because my computation probably wrong. This is 2/3. I put 1/4, and then 1/3 I put 8. So this is incorrect. In my side, it's not correct. So yours is correct. Okay,
Okay.
Lexian, this is good. Excellent.
Okay, thank you, sir.
Mm.
Can I see your answer?
My answer, yeah, of course. My answer is incorrect in that case.
Can you share your screen, sir?
Sure. I think I mistaken it. Put 2/3. Can you see this?
Mm-hmm.
2/3 become 4, and then 1/3 become 8. So this must be reversed, right?
Yeah.
Yeah. So it's incorrect. So yours is correct.
Okay.
Okay. Okay. It's okay. I can read. I can fix this later. Huh?
Okay.
Yes. Yeah. So don't forget to claim your citation.
Okay.
Okay.
Mm.
So I'm not always correct. Okay. That's okay. So I can correct it. No problem. So Stefan, Dan, Davin, Taran. Taran number 10 is easy. Oh.
Wait, sir, for a moment. Mine is
Yeah.
the hardest. Wait, yeah.
Yours is the
Wait, sir.
hardest, is it?
Number 8.
Number 8. 7 is quite hard.
Yeah.
Yeah. Oh, yeah. Number 8 is the hardest. But this is actually easy, Dafin, because this is
Yeah,
uniform distribution.
not that hard, actually.
Yeah, this is quite long. Yeah. Number 9, Cedric. This is the problem is the cloud only. Once you solve the cloud, this is easy. Okay. Number 10. Taran, super, very, very easy. The number 10. 11 is hard. Lexan, can you try number 11 also?
Where, sir? Can you show me? I will screenshot it.
This one.
Hmm. Kenapa kok itu apa di tabel nggak langsung di note-nya sih?
Hmm? Di tabel berarti note-nya terlalu banyak. Too many.
Okay. Okay, sir.
Okay, let's try. So
Okay, sir.
11. So if you want challenge, you can go number 12, 13. Okay, that is getting harder and harder. And 14. Yeah, you want challenge. 12 is rather hard. So, section 11. Taran, can you do number 10?
Oh yeah, sir. Just one.
Yeah, okay. So then now you do number 11.
Iya, not yet.
Okay,
Belum selesai.
okay.
Terus
Ah,
step itu just multiply by 300 aja kan. The clue.
okay. No, you assume first. That's the clue from me, but you can use different numbers.
Yeah.
That's only the clue from me. But you can assume different numbers.
Um,
Is Tiara with you? So let her also do this.
yeah, and they've also.
Oh yeah, this is a good practice, yeah.
Oh.
Iya. Dia mau help. Help, guys! Please help me! Help!
Last time they don't have this yet. This is new slide.
I'm confused. I'm tired. Oh, go sleep. Oh.
You know what you need to do if you are tired, you just type this in Excel and then you just put n underscore stochastic to ideal flow, you will get the result.
Okay. Stochastic matrix.
Yeah, you just type the stochastic matrix. You want me to show you?
Yeah, sure.
Okay.
Let me follow.
Okay, let me get the example of. Did you see my Excel?
Yeah.
Okay, let me get that. Okay, so this S, I have A, B, C, D, isn't it? A, B, C, D. So I have S, then A, B, C, D.
One mic.
So this one 0, this is 0.5, this one
So I
5,
think your Excel is freeze.
please. Is it okay?
Nah, ini baru benar.
Okay. So B, I just type, 0, 0, 1, 0, right? Third one is 0, 0, 0, 1. Is that correct? And then the third one is 3/4, oh no, 0.75. Oh no, 0.75. And then this one is 0.25. And then this is 0, 0. Is that correct?
Yeah.
Okay, so I'll just copy this and I will put it here. So I will put this F, ideal flow. I will delete this. Okay. Is that okay? This is the input, right? That you have.
Yeah.
Yellow.
Hmm.
You see, or shall we give name?
Yep, stochastic matrix.
Stochastic matrix. So I will put this S. Okay, S underscore. Is that okay?
Yeah.
Okay, so I need to have total flow. Okay, so I have no total flow, so I will put okay, I put 100, no problem. Any number later can be fixed up. Okay, so here N underscore, can you see?
Yeah.
Stochastic ST, stochastic to ideal flow. Can you see this? And then
Okay.
a tab, okay, and then this one, and then this one. Okay,
Bukan 300 ya? No ya? The total flow.
later.
Okay.
Just put any number, no problem. Okay, close, and then here, okay, you highlight, you select.
Control Shift Enter.
No, click this one first, and then Control Shift Enter.
Yeah.
Okay. Now, what do you want? You want flow in node A to be 300. Okay, so I will put sum here. Right? This is the sum. Okay, so I will color it differently so that green. Okay, again, this is the sum. Okay, the sum of all of this. Okay, this one must be, oh, the total is the same, yeah, 100 and 100. Okay, so I will put this color green, except this one I will put color blue so that I will know that this is the, okay, I will put color orange. So what we want, node A, this one must be 300, right? Okay, what we will do is here, you go to data, what if analysis, goal seek, set this to be 300 by changing cell, total flow, yeah. Da-da-da-da, I got that. Can you see?
Okay.
Okay.
What did you do that, sir? Yang terakhir,
Eh,
the last one, preview.
the last one?
Ya, yang apa? Total cell change to 300.
Okay, so initially I will put 100, right? Any number actually. This is initially.
Yes.
So what we want? We want this one to be 300.
Yes.
Oh, then you go to data, what if analysis, goal seek. This is to calibrate, okay?
Yes.
The value in here, the P, yeah, the sum is 300, right? So I put 300 there. Can you see?
Hmm.
So I put the value to 300 by changing cell. What the cell that change? The parameter is this one. Total flow, isn't it?
Yeah.
So click OK. There is compute.
Okay.
Okay.
Hmm.
So now if you want to make this into integer, so if I divide this by 10, there I got that. So can I divide by what? Can I make it minimum? So I can divide by 15, this one.
15. Cannot 5 gak sih?
I divide by 15, what will happen? Oh yeah, cannot. Okay.
5 kayaknya.
By 5. Okay, let's divide by 5. Oh yeah, by 5. That's correct. So this is the minimum. The minimum integer that we can get.
Okay.
Okay, nice. So
Sir,
if you can do one, yes, try to do manual.
I tried to use your function
Mm-hmm.
to help solve mine.
Mm-hmm.
I got a little bit confused. Can you help me?
Sure. You share your screen, please.
So this is what I did. exactly the same like you. But this one in your I I put 0.5 instead of half.
It's the same, yeah. The same.
Yeah. So
Wait a
then
minute.
you in the slide you said change
Uh,
node to 4.
I think we have different. Oh, this is what? This is number.
This one.
Oh, okay. This is number 9. Wait, this is different problem. Contoh mate. This is number 9, right?
Mm-hmm.
Mm-hmm. Okay, so you have that. Okay, so you have A to B half, and then A to D also half. Is that correct? Oh, can you share your screen?
Oh, I already share. Okay,
Really?
I will stop again. I will share again.
Yes.
Oh, can you see this now?
Wait.
Can you see it, sir?
Yeah, I'm seeing. Okay. Can you check if this is correct, the stochastic?
This one.
Okay, so 1/4, 3/4, okay. And then if you color it, that's easier. But
This
anyway,
one. Which one should I color? So this one.
okay, yeah, that one. Okay, I think this is correct, right? Okay,
Mhm.
so then what you will do, go
I did
to
this.
K with yeah, you can color that also. Okay, let's see. You have stochastic to ideal flow. Okay. Okay, you have R2022. Okay. So, okay, can you sum P, what is it? P35? Can you get the sum?
P35.
Hmm.
This
Can you
one
get,
equal.
yeah, the sum of all the flow,
This one.
the one that green.
Oh, like this one, sir.
Yeah, close.
And then,
Okay, that's correct. Okay, so in
but
that
this one
case,
is not ideal.
oh, ideal, of course, is ideal flow, right? Not the same. That's strange. Are you sure this is correct? Can you
Uh,
go to K29?
K29.
Oh, you did not make it yet. That's why.
Oh, what's the wrong one, sir?
Oh, okay. So, okay, go to K29.
This one, K29.
Can you click? You go
This
to
one,
K. Okay, click in. No, K29. K30, sorry.
K30.
No, just click in K30 without this.
Okay.
Okay. So you hold
Yes.
your shift button.
Shift
Shift
button.
button, you
Shift.
press. Yeah.
Mm-hmm.
Okay, there. And then you click this part.
This one.
Yes. And then shift
Mm-hmm.
control enter together. There. No.
Still not the.
Again, you go here,
Yes.
okay, and then you select all the green part,
Mm-hmm.
okay, and then you use mouse click here, okay. And
Should I highlight, sir? No.
no need, just and then you hold shift and control together, and then you press
Yes.
enter.
Enter.
Shift and control and enter. Okay.
Okay.
So probably. So can you fix this and fix this? This one must be the sum of here. This one must be the sum of above. and
This
then
one is
copy.
830 until 834. No change. This one,
You did not copy.
oh, still the same, sir. This
Oh.
is this one is
Okay,
strange.
oh, strange. Oh, no problem. So let's check. Maybe your network is incorrect. So can you type here equal n
Equal n
and underscore
underscore
is
is I
irreducible. Is
is
irreducible. Irreducible
equal
of this yellow.
true.
Oh, true. Okay, if this is true, this must be premagic. Why this is not premagic? Correct, 50-15, 50-15. Oh, the third one is strange, this one. Why you have 0?
Yeah,
Well,
that's
you have 24.2. Why the sum is 0? Your sum is incorrect. No, this sum, can you use this sum? Can you go
830.
there?
Yeah,
Click that one.
equal
Oh, no, no, no.
sum.
Let you get the sum of this all from K until O.
So equal sum.
Yes. Of
This one
that one
until
until O.
oh
Okay, enter. And then copy this down.
oh there.
Only the sum is incorrect. So, but you can test here also, n equal
And
n underscore is ideal flow.
will flow. This
Yeah,
one
and then the green one. Oh, true.
there. Okay.
Only your
But,
sum only a while ago.
mhm.
Okay, so it's correct. So now
Okay.
you want to get it integer, right?
Yes.
How to get the integer? You put this, okay, into fraction. Yeah, you go here, number format.
Mm-hmm.
The
Fraction.
here
Fraction. Oh,
fraction three digits.
fraction 3 digits.
Oh, so now you calculate the the LCM. What is the LCM? Here you calculate the LCM of 8, 7, and 4.
Dengan equal
Yeah.
LCM
LCM of 8, 4, and 7. What is that?
8 4
7.
this.
56. So let's try
Mm-hmm.
with this 56. What will happen?
Uh-huh.
Oh, still you have 5, 2, and 7, and 3. So you need to find the other numbers which make it, in my case, this is supposed to be simple. How much is this? 16 plus this is 20, 29, 30, 33. I put it 33. Can you try 33?
Oh, there.
No.
Oh, okay. All good then, sir.
Yes.
Okay, nice.
Nice.
Should we finish, sir?
Yeah, okay. Finish now. Yeah, thank you very much. So see you next year.
See you next year, sir.
Yeah.
Thank
Thank,
you.
Next
Thank
year?
you,
Thank you,
sir.
sir.
Thanks very much.
See you next
see
year.
you
Safe
in
flight.
the next semester.
Okay, let's
Alright.
go.
Bye.
Bye-bye, sir.
Bye-bye.
Goodbye, sir. See you in the
Bye.
next semester, ya.
Okay.
Have a nice day.
You too.
Okay.
Bye-bye.